formatting. So, no. All right. So let's do the transitive closure again, so that we all understand what's going on. So, does everybody understand the problem? Right. First, think of these pairs as, the best way to think is their places, and you can reach from 1 to 2, but you can't necessarily reach from 2 to 1, right? So if you can reach from 1 to 2 and then you can reach from 2 to 3, it means that you can also reach from 1 to 3. So we want to see all places, all the pairs of places that we can travel between, right? In whatever direction. So I'm going to add here the intermediate result. So I'm going to say intermediate. And then I'm going to say result. And then we want to see how this is growing. Okay? So that hopefully will give you a better idea. So I'm going to take this and transfer it here. And then let's just copy. Let's take this one, which is one that is not overly big, but has interesting things. Okay, so this one seems to be an interesting one. Okay, so notice what happens in the first round. So we're taking the cross product of all these elements in the set, right? We're creating all pairs of pairs, right? And if the destination of the first is equal to the source of the second, then we can add the fact that we can go from the source of the first to the destination of the second. Does that make sense? Right? So let's look at what we added. So we already knew that we can go from 1 to 2 and from 1 to 3, right? These were there already. From 1 to 4, so this is exactly the first one, right? There's no difference. It's just that it has more spaces, right? So let's look at the first step. So we knew that we can go from 1 to 2, from 1 to 3, 1 to 4 was there, 2 to 3 was there, 4 to 2 was not there, right? So because we can go from 4 to 1 and from 1 to 2, right? Now it appears that we can go from 4 to 2, right? 1 to 2 was there, 4 to 4 was not there, right? So because we can go from 4 to 1 and then from 1 to 4, it must be the case that we can also go from 4 to 4, right? And so on. 4 to 3 was not there, but we can go from 4 to 1 and from 1 to 3, right? So this one appears here, right? And 4 to 1 was there, and 1 to 1 was not there, but we can go from 4 to 1, from 1 to 4 and 4 to 1, right? 1 to 4, then 4 to 1. So it must be that we can go from 1 to 1, right? What's going to happen next time? Next time I'm going to take this set and see if I can extend it. What do I want to extend it with? So you might think of two possibilities, right? I might extend it with the original set, or I might extend it with itself. Which one is the proper one? With itself or with the original one? With the original, right? Why? Because you'd still get reachability, right? But you're going to get reachability in 2 steps, then reachability in 4 steps, then reachability in 8 steps if you do that, right? You will miss the 3 steps, the 5 steps. Does it make sense? So we're extending it with itself. So we're looking at this one, and we try to extend it with itself, right? So for instance, we're gonna say, oh, 1, 3, right? And I'm going in here. There's nothing starting at 3. So 1, 3 stays the same. 1, 4, right? Well, if I look carefully, there's 4, 1, which means that from 1, 4 combined with 4, 1, I can go from 1 to 1. But 1 to 1 is already here, right? So as I add it to the set doesn't extend. So you're going to see that if we try to create all these combinations, we're going to get a set that didn't change. And this is going to be our stop condition, right? If we try to extend the set, but the set didn't grow, it means that we have reached the limit. Nothing will be added ever again, right? So this is the result, and this is precisely what we print here. Okay? This is what transitive closure means. Okay? Now, let's look again at the code and try to understand the code. So we need to create a Cartesian product, right? What's a Cartesian product? So later we're going to learn. Let me see if product is here. So from okay. So if I say product of 1, 2, 3 and 10, 20, 30, and we turn this into a list, right? Look at what we have obtained, right? All the pairs. How do we produce this very quickly? Let's say we didn't have product. How do we produce this ourselves? For, again? One, two, three. Y in 10, 20, 30. Right? So I'm going to say print x, y. Why? Because we don't know yet how to produce iterators. We're going to find out later, right? So we can produce all the pairs. So it's a similar process in which we essentially produce all the pairs, right? So we're going to have two nested for loops that allow us to produce essentially the Cartesian product of the candidate result and the original set, right? Now, let's do this again, but I'm going to do this with 1, 2, 3, right? So now, what happens what happens if I make all these into pairs? 1 and 2, 2 and 3, and maybe 3 and 2. Okay? Again? Because I can, because I choose to do it that way. For no good reason, but that I want to pick an example. So let's go here and put the same set, right? And I'm going to do again print x1. So now notice that what we have is pairs of pairs, right? And notice that some pairs, for some pairs, the destination of the first pair is equal to the source of the second pair. Happens here, happens here, right? It happens here. All right? So let's now add one more thing. So I'm going to print only if x1 is equal to y0, right? Does it make sense? Right? So now I actually don't want the entire pair, right? I just want the source of the first and the destination of the second, right? Is that okay? So I'm going to say x0, y1. Right? Why? Because if x1 is equal to y0, it means that I can reach from x0 to y1. Yeah? Right? So if these are my two sets, right, this says that we can reach from the first to the second in 2 hops. Right? In 2 hops. So I want the reachability in any number of hops. Okay? Not just in 2. If I'm going to go one more round, so if I'm going to take, so if, now one thing I can do is keep this the same, but the second set, instead of using this one, right, I could add this stuff. Right, I can say, oh, now I also can reach from 1 to 3, and I can reach from 3 to 3, and I can reach from 2 to 2, right? Yes? So I want reachability in 1 or 2 hops. So this list is 2 hops. This list is 1 hop. So if I union them, if I put them together, I'm going to get 1 or 2 hops. So if I do this, I'm going to get 1 or 2 or 3. No, I'm going to get 3 hops, right? So I'm going to put this here. So this is going to be 2 or 3 hops, right? So this is 1 or 2 hops, right? This is 1 hops. This is just 1 hops. This is 1 or 2 hops. Right? So I'm going to get 2 or 3 hops. Right? So this is 2 or 3 hops. So now I can do what? I can take these, add them to this guy, and I'm going to get 1 or 2 or 3 hops. So next time, this guy, I'm going to inject all these ones into here, right? And what's going to happen? I'm going to keep adding and adding and adding until at some point there's nothing to add anymore, right? I keep running, but I'm not getting anything new. At which point, that is reachability with any number of hops. Okay? So let's go back to the code and see how that works, right? So if you look carefully at these two for loops, they're exactly the 2 nested for loops that you have seen. Okay? Now there's a new feature that we're experiencing here, which is pattern matching. So previously this was X instead of A and B. And then X is a pair, and I can use x0 for the first component and x1 for the second component. All right? Instead of doing that, I can use two variables, two names here, and A is going to be the replacement for x0, and B is going to be the replacement for x1. Makes things easier to write, right? So we are saying that A and B match the pair, A becoming the first component or the 0th component, and B becoming the first component. Is that clear? The same happens here. Notice that this is the destination of the first pair. This is the source of the second pair. If the destination of the second pair and the source of the first pair are the same, then we can go from the source of the first pair to the destination of the second pair. So instead of printing, which is what we were doing previously, we grow our set. Okay, instead of saying print, we're saying, oh, put this into the next round, the next candidate. Okay? Add this to the next candidate. Right? So we're going to do this many times. Until when? Until the result is the same as next. So we started with result. We produced next. But in producing next, we didn't manage to add anything to the result. So at this point, we can stop and we return the result. Does this make sense? Right, so we're checking the result. If result, as long as, so we have a while here, right? As long as result has not been the same as next, we can do one more round. Right? So at the point when they are the same, this becomes false. As they become false, we exit the while and we go to return, and we return whatever result we have computed up to that point. Cool? So now you're ninjas. You have seen a piece of code with 3 nested loops. All right? One loop, 2, 3. Okay? Now, these A and B's, we've seen them as numbers, but it doesn't matter what they are, right? So what we need is a set of pairs. The elements of the pairs, it doesn't matter what they are. They can be numbers, they can be strings, they can be booleans, they can be other collections. Okay? All right. So the next thing we learn on sets is mutation. We learn how to change them. So sets are mutable. They can be changed. Right? Remember, mutability is not always desired. Right? So that's why we have immutable collections like the tuple. Okay? So for instance, if I'm going to have a set S and I'm going to add a new element to it, that element will appear inside the set. Remember that the order of the set is not important, and when the set is printed on the screen, some random order will be used. Okay? We can also remove element from the set. So there's this method called discard. All right, and I just use the word method because it is used here. Procedures that are stored inside an object are called methods. It's an object-oriented programming thing. All right, so it's just a procedure, but it works on this set. All right, so when I say s dot discard 1000, then the element 1000, if found, is removed. Okay. Now, what if I try to remove an element that doesn't exist in the set? That's still fine. There will be no error. All right. So there will be no error, and in this case, the set will not be changed. So we have to distinguish between these kinds of procedures that don't fail, that essentially do their work silently, right? Don't fail if a condition is not met, right? So, because if the procedure fails, right, your entire program might fail, right? So failures cascade. They go from one level to the next, so from a small procedure to a bigger procedure up to the main program failure, right? Fail. So you don't want your program to fail. And we're going to learn how to handle failures shortly, right? But sometimes, so you always have to wonder, right? I want to remove an element. So in your mind, immediately a little bulb has to start flickering and say, oh, what if I try to remove an element that is not in the set? What happens then, right? So you have to go and ask that question. And sometimes it will fail, right? There will be an error message, and your entire program is stopped. Sometimes nothing happens, right? It depends on the person who designed that procedure. Certain things are done traditionally in certain ways, right? So for sets, this is the standard. It is the same as in the case of the sum of a list is 0 when the list is empty. There's no good reason for it, right? It's convenient in certain cases, but there's no good reason. It's a convention, right? But it's been there for 50 or 60 years of this profession existing, right? So ever since computers were being programmed, people came up with the set of a collection, of an empty collection. The sum of an empty collection should be 0, right? So it's been like that forever. Then you have to accept it and be consistent with it. All right. Now, I was telling you that some operations fail and some don't, right? Now, there's a similar procedure called remove, also on a set, right? So it does the same thing as discard when the element exists in the set. But when the element doesn't exist in the set, then it bombs. It yields an error. Okay? So in this case, sets give you a choice, right? And sometimes it is important to fail the program. Or sometimes it is important to signal the fact that something is not working well, right? Typically, you don't want to fail the entire program, but you want to fail this component and allow the higher level to handle that, and we're going to see how that can happen. All right. Yes. Update will perform a union in place. Right? We have seen the union of two sets. There is the operator bar that takes two sets, produces a completely new set, while the old two sets are unchanged. The update method will take another set and change the set on which it is called. So this S is changed after the operation. There is an operation called intersection update, which will do that with the intersection. So we'll update the current set with the intersection of the two sets. right? Again, remember there is an operator called intersection, represented by the ampersand, which produces the intersection of two sets without changing the operands, right? So you have a choice. There's the same with the difference. Oops. And we also have the pop operation, all right? So certain operations are provided for consistency. Lists have this operation, right? We can do a list.pop, and that will remove the last element, okay? Now, it is convenient to have an operation that removes an element from a collection. For the set, we don't have a specific order. So what will happen is we remove a random element. This is still useful, all right? Because often enough, we want to process each element exactly once. So we will remove elements. It doesn't matter the order, but we remove the elements. We want to be sure that we touch all of them, and none is left, none is processed twice. So this pop will help us with that, right? So it's very similar to list, just that we don't know what's being removed. Update performs union, right? So the old S is this. So when I say update, I'm going to add these elements to S, and you see all of them, right? 4,000 is here, 1,000, 2,000, 3,000, right? So all the elements are there, just that they're in random order. What do you mean by join? Right? So if I have A equals 1, 2, right? And B is defined as 3 and 4, right? If I compute A union B, I get this, but A is unchanged, B is unchanged, right? On the other hand, if I say A.update B, now A is changed. B is unchanged, but A is forever changed, right? The 1, 2 that was there, I cannot recover it anymore. Okay? So the same can happen with the, actually I can recover it in this case, but I can just say A.update, difference update, right? So I can get it back. But it doesn't always work like that. Okay? So let's produce the list of subsets, which is also called the power set. Have you heard of the power set?
No.
All right. So let's say I have the set 1, 2, 3. What I want as a result is the set of all subsets, or the list of all subsets. So one subset is the empty set, then 1, then 2, then 3, then 1, 2, then 1, 3, then 2, 3. Then what's left? One, two, three, right? So I want to produce this, but for any set. Okay? So this is where pop will come in handy. All right? So this is a recursive function. If S is empty, and this is typically how we check the emptiness of any collection, right? If you check online, if you look online, you're going to find out that there's the Pythonic way of doing things, right? And more seasoned programmers will say that this is idiomatic coding. So you can do things in many ways, and programming languages give you a lot of power, and you can do things in many ways, right? But, with great power comes great responsibility. So you shouldn't use that power extensively, right? So communities have come with sort of standard ways of doing certain things, right? And for Python, they call them Pythonic. But for most languages, seasoned coders will say that it is idiomatic coding, right? You use an idiom of the language. You don't use the full language. So checking that any collection, sets or lists or anything is empty is done in this way, checking whether the length is 0. And you're going to be surprised to find out that a set has a length. It doesn't seem reasonable to call the size of a set its length, but it is like that in Python. So if the set is empty, we return the list containing the empty set. The only subset of the empty set is the empty set. So we return the list containing empty. Otherwise, how do you obtain the set of subsets? Well, I'm going to go back here and right. Let's say I have the set 1, 2, 3, right? And I'm going to remove an arbitrary element from 1, 2, 3. Let's say that happens to be 2. I don't know which one it would be, but let's say it's 2. So I'm going to be left with the set 1, 3, right? Let's say I compute now all the subsets of 1, 3. And we know what they are, right? But in recursion, we always assume that if the problem is of smaller size, if the input is of smaller size, we magically know how to solve the problem, right? So we assume that our set is 1, 3, and let's write it like this, set, and then we get all these subsets of 1, 3. Right? These are all. What is the relationship between this and this? Can we obtain one from the other? Because this is actually the result we want. What I have just highlighted is the result we want. What's the relationship? So that's one very good observation. So the first thing we notice that this is a subset of this. Okay? So I can start with this. Let's not put the carriage return there. And I can union it with what? What's left? What would be left? Actually, I can't union. I have to append. What's left? Let's look at what's left. So 2 is there. Set of 1 and 2. The set of 2 and 3. So now what's the relationship between this and this? Do you see a pattern? If I remove 2 from each of the elements of the second list, 2 removed from here, 2 removed from here, 2 removed from here, 2 removed from here, what do I get? The one on the left, right? So all I have to do, so we already assumed that because 1 and 3 is smaller, we know how to compute this, right? So what do I need to do? I take this, and I take another copy of this, and I insert 2 in every element in there, right? And then I get the result for 3. And if I want to go to a set of 4 elements, I'm going to take the result for 3, and I'm going to do the same thing. I'm going to take that result, then duplicate it, And in the second copy, I'm going to insert the fourth element, right? And it doesn't matter which element I pop in the beginning, right? So I'm going to extract an element, solve the problem for the smaller size, then take that result, duplicate it, and in the second copy, I'm going to insert the element I popped. Okay? That should give me the result. Okay, so let's look at the code. What do we do? As I said, pop first, right? Then magically get the result for the smaller size, right? So now we do two things, right? So for each element in a copy of L, right, I will take L and I append it with what? Well, this A is missing the popped element, right? So I put it back. Make sense? Well, we just discussed how else would we do it? We just discussed the strategy here. When we were here, we discussed the strategy, right? So now I'm implementing it. How else would we do it? So if you don't pop it, then you have a problem of the same size. Then induction doesn't hold. So the recursion doesn't hold, right? So the entire scaffolding of recursion relies on the fact that my recursive call is on a problem of smaller size. I have to make the problem smaller, right? Remember Towers of Hanoi, I'm going from n to n plus 1. If you remember Fibonacci, I'm going from n to n minus 1 and n minus 2 respectively, right? The size needs to grow, right? So if I'm going to make a recursive call, whatever I put here has to be smaller somehow. So a very simple way of making it smaller is pop an element. Now I have a smaller set. Now that's a valid input for the recursive call. Clear? So let's see this working. Actually, I should go here. So we get the result that we wanted, right? It will, of course, work with any kind of element. So let's say A, B, C, D. How many do we get in general? Well, let me. It's easier to do this, right? If I remove one, it's going to be 8. If I remove another one, 4, right? Are you getting a hint? How many? Louder? To the power of n, right? That makes perfect sense. Why? Because I'm taking 4 here, and I'm compelled to add 4 more, right? So I will always double the size of the previous round, right? So with the empty set, I have 0 elements initially, and the list will contain the empty set, which is 1 element, right? So to the power 0, which is 1, and then it doubles, right? 2, 4, 8, and so on. Okay. Now, so there's a very interesting aspect to this function, right? So let's create a list and see. Let's actually, instead of calling it like this, let's give it a name, right? Let's put a name to it, S. And now let us call list of subsets applied to S. And this returns a very nice result. Now, what should the value of S be? What would be your expectation? Should S have changed? Again? Well, if I evaluate it now, what do you think will happen? What am I going to get? Am I going to get the original set? You see here, S was A, B, C, D. Am I going to get the same thing? Yeah, so at least you would expect that, right? Not true. Yes. So so the question is, so it happens, right? Obviously, because we pop everything, right, element by element, we do these pops one by one by one. In the end, we're left with nothing, right? So is this something good? No, right? So again, with great power comes great responsibility, and we just misused the power. We had the power to empty the set. We did it, and nobody expected we would do it. Right? So, what should we do in that case? What should we be doing? Again? Yes. Right? So instead of using this as a list of subsets, I'm going to define a helper as copy. Again? What would I give you? That was in that case, right? That was in that case where the sets were disjoint, right? And then we would do okay. So this solves that problem. So we have to be very careful. Often mutability improves performance, right? But the improvement of performance is now no excuse for code that performs unexpected things. Right? So why? Because I mean, if I give this function to you and your users, you won't. One thing that you don't want you to do is have to understand the code. You have to understand how to use the code, not to understand the code itself. Right? It's the same story of abstraction that I was telling you a while ago. When you don't want to understand how a car is built to drive it. Right? It makes no sense. If you have to become a mechanical engineer, drive a car, nobody would be driving cars, or only the mechanical engineers would be driving cars, and there's very few of them, right? So that's an important principle. Write code that is easy to use, that performs expected things, that doesn't surprise anybody, especially doesn't surprise anybody unfairly. Okay? So with sets, we have the usual conversions, right? A set can be converted into a list. So remember that the order is random. It can be converted into a tuple, exactly the same problem, right? And then it can go in the opposite direction. Anything can be converted into a set. But the order is lost and duplicates are collapsed together, right? So if there are multiple instances of a value, there will be only one instance left in the set. Okay? Questions for sets? Or fine? So the next thing is dictionaries. Okay. So sets are actually a special case of a dictionary, right? We discussed them first because you know about sets from school, from elementary school, but they're just a special case. All right. So what's a dictionary? It's a mapping between a key and a value. All right. Um, think of what the dictionary in real life is, right? So you have the word and the explanation of the word. You have a relatively efficient way of finding the word. So that's one important thing. We have a relatively efficient way of finding the word, which is the key in this case, right? And the value is the explanation for the word. In general, what we have in a dictionary as it is in Python is not an explanation as a value. We have any kind of mapping, right? So what we can store is an association between a key and a value. And we have a very efficient way of finding the key, much more efficient than the one that we have in real-life dictionaries, right? Because in real-life dictionaries, we pretty much go, we perform binary search, right? So we kind of guess what it is, and then we follow the order. We rely on the fact that the whole set of keys is ordered. There is a much better technique called hashing that we don't have time to go into that allows us constant time. So instead of looking through the dictionary and flipping pages, it's as if we always open the dictionary at the correct page, right? So there is such a technique. So dictionaries are very efficient in creating associations between two objects. Obviously, in order to do that, the key has to be unique. All right, so that's a property that it shares with the sets. So if you look here, there's an example, right? And notice that a dictionary appears to be a set of pairs. The pairs, it's not the classical pair as in a tuple. It's a dictionary pair, right? Which is two elements separated by colon. So the first mapping is A mapping to 3.5. The second mapping is 2 mapping to XYZ. The third mapping is 3 mapping to 4. The last mapping is 4.5 mapping into the string Python is 5, right? So we have a set of mappings. That's why we use curly braces. The order of the mappings is not important, but the mappings themselves are, right? So you can think of this as an atomic value, right? That's the mapping. The unit of the dictionary is the mapping. It always has two pieces, the key and the value. So always when we give a key, we can retrieve the value. All right? So for instance, if I say D indexed by the key A, right, we're going to get back the value associated with the key, which is 3.5 in this case. All right? This, you can put in this a billion mappings easily. And it is as fast as if it only has 10 mappings. It's no difference, right? It's a fantastic type of collection. All right? Now, a dictionary is not very different from a function. If you take a function like sine, what does it do? Put an argument, get a value. Put in another argument, you get another value, right? Possibly the same value, right? The values don't need to be unique. The keys need to be unique, right? Put in the first value again, the first key again, you get the first value again, right? So sine is an association between a specific argument and a specific value, right? We have a full set of pairs, right? Argument and value. So the dictionary is no different. Just that the dictionary is discrete. All right? If you have placed the mapping inside, then you get it back. If you didn't place a mapping inside, then you're going to get most typically an error. right? So again, we're going to have membership, both with errors and without errors. We'll see in a second. Keys don't have to be of the same nature, right? But they have to be indexable. And not everything is indexable, all right? But primitive data structures like numbers and strings are indexable. Everything that is non-mutable in general is indexable. Then tuples of such things are indexable, right? But not lists and not sets, right? They're not indexable because they are mutable. Okay? Dictionaries are mutable. So in that sense, they resemble arrays to a certain extent, right? So I can change the value. So previously, D indexed by A was 3.5, right? You see it here. You see it here. But now I want to change that, right? So I can assign a new string to a key, and the mapping gets replaced. Okay? All right. So it is very useful when you want to essentially create a function bit by bit. Okay? You don't have a function as a computation, but you have a function for which you figure out, oh, for 1, I have to return 3. And then for 5, later I have to return 6. And then you add these mappings one by one to the dictionary. All the functions that the functions that work for collections work on dictionaries as well. And what happens is that what are we going to take? We have pairs, right? So if I'm going to apply, for instance, the max, what will I be taking out of the dictionary, right? And the default is always to take the keys, right? So if I apply max to di, I'm going to regard di as the set of keys. If I'm going to do min, the same. If I'm going to do the sum, the same. I'm going to use the set of keys. So by default, whenever I put a dictionary in the place where a collection is expected, right, automatically the dictionary becomes the set of keys. Okay? So that's sometimes useful. Right? So if I'm going to do for k in D, right, D is a dictionary, but I use it as a generic iterable. Remember, the for loop expects a generic iterable. The question is, what am I going to print here? And the letter k that I'm using suggests that I will be getting the keys. Right? The values. Yeah, so it's a matter of convention. One thing you can do is write to Guido van Rossum. One thing you can do is write to Guido van Rossum. You know who Guido van Rossum is? It's the creator of Python, right? And tell him that you don't like this feature. That's one thing that for which there was a lot of discussion, right? There are many discussions on various features of Python, but you see, the guy is benevolent dictator for life, right? So he dictates what he likes about language, and this has been decided already. Okay. You definitely don't want both keys and values, right? You have to select either keys or the values. You can obtain the iterable of values if you want to, right? So it's obviously possible, right? The thing is, so if I say, for instance, d.items, I'm going to get the pairs, right? And there is also d.values. I think we have it somewhere. Yeah, you see here. But it's more to write. So the question is, right, this is the easiest thing you can write. Right? This is the easiest thing you can write. So you want the language to be concise, and you want the defaults to be well thought out, right? So many people would say, oh yes, I want the values. It makes sense to have the values, right? Well, if that's what you want, you're not in luck. With this one, you're not in luck. That's what I can tell you. All right. Nevertheless, right, what you want is possible, and that's important. That's the important thing in the end, right? So you see that if we do d dot items, we're going to get the pairs, key value pairs, right? So as before, we can match two variables on the pairs, on the tuples, right? So then k becomes the key and v becomes the value. So we can, for instance, print both the key and the value. We would get something like this in the print. Okay? We can remove keys from the dictionary, remove them completely with this, right? And we have, I'm not sure. I think we have a way of deleting them. Deleting them without an error, right? So this will produce an error if the key doesn't exist, right? I can't remember whether there's one that's silently, that is silent with respect to that. This is membership. So it tells you if the key is in the dictionary. Okay. We can get an iterable of the keys, and this is what will be printed out, but it is an iterable. You can use it in a for loop. We can get an iterable of values. All right. And then you can get an iterable of pairs. So notice what we get in here is a list of pairs, each pair containing the key and the value, a key and value pair from. Okay. Now we have access with error. So if we try to access a key that doesn't exist, we get an error. Or we have access without error. So if we use d.get, right, we get none when there's no value corresponding to that. Okay. We can also get a default value. So we say d.get 1000. If 1000 exists, we get the value. If 1000 doesn't exist, then we get the return value is this. So we get to set the default value. Okay. Update works pretty much like for the set, right? Just that the element now is a mapping, but we don't have a syntax for the mapping. So then the way to do it in Python will be to add pairs, right? So this pair represents a mapping from 1000 to 2000, and this pair represents another mapping from 3000 to 4000. Okay, so it's very similar to set now. Is that clear? So if I were to use the dictionary to implement a set, how would I do it? I will go from key to which value? Because all I want is the key. So I want to implement set. Well, let's say that my language, that Python didn't allow sets, but it does allow dictionaries. Can I have sets? And how would I implement sets? Just get the keys, but I need to provide values. So what would be those values? Could be anything, right? But we want some sort of standard choice. So a very good, again? Can be the key itself. Is it easier, for instance, if it's true? Is the value true? right? All the values are? Not necessarily, right? No, so if I have a dictionary whereby, for instance, I would have, for instance, a, a, two, 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 right? So this is something that gets me essentially the set of A and 2, right? Yeah. So a dictionary provides enough functionality to implement sets. That's the essence, right? And thinking of that, sets are very similar to dictionaries. Sets and dictionaries have a lot in common. Okay? Just think of the dictionary as being a set of mapping. A mapping being a pair of two things. Okay? We have a pop, and we're going to extract an arbitrary mapping. Right? So there's a problem with this pop because it only returns the value. It doesn't tell you what the key was, right? So it removes a mapping, but it only returns the value of that mapping. The key is lost. So to fix that, there's another function called pop item. Pop item returns the pair representing the mapping, so you also get a handle on the key. Okay, so what we typically want to use a dictionary is to have a mapping from a key to a value, and a very common one is one in which we have words or characters or objects, and we have the number of occurrences of those objects in some collection, right? So we haven't learned how to parse words. A very typical application is to count occurrences of words. How many distinct words do we have, and how many times each of the words occurs in a text, right? So we don't know how to do that yet because we don't know how to parse text. But if we have a list of numbers, or if we have a list of elements, we could count how many times each of them occurs in the list, right? So let's try to do that. So we have this count items function or procedure, all right? And we start with an empty dictionary, all right? And then we iterate through all the elements in the collection, right? So E is the element and becomes the key in the dictionary. The value will become the number of occurrences. Okay? So the dictionary is initially empty. When I see this E, it may be the case that E appears in the dictionary already or doesn't. If it doesn't, we're going to take a value of 0. Because if it doesn't, it's as if the word occurred 0 times in the text so far, right? And we're going to increase that number by 1. Right? We just encountered E. So since we have seen one E, I have to increase the number of occurrences, right? So we do this until we exhaust the iterable and return the dictionary. Okay? So if we're going to run this, we're going to get this back. Possibly in a different order, right? The mappings may be in a different order. But clearly, 1 appears twice. So this 1 appears twice. You can see it highlighted. 2 appears 4 times. Right? 3 appears 4 times as well. 4 appears 3 times. 5 appears twice. Clear? Again? Why it would be? So this is the list. You see, this guy becomes the IT here, right? So then this E will take turns in becoming 1, then 2, then 3, then 2, then 4, then 5, then 3, then 2. All right? So this E will take turns in becoming each of the elements in the interval. So having one occurrence of E, one E, what am I going to do is, let me get the current number of occurrences for E. All right? So that number is, if E is already in the dictionary, I'm going to get whatever number is there. If E is not in the dictionary, it means that the number of occurrences of E is 0, and I'm going to return 0. Right? And since I have just encountered E, I am going to add one more occurrence. Okay? And I'm going to put this value back in the slot corresponding to E. Okay? Right? Remember, I can change the value of a key. So this is my new value, which is the old value plus 1, and I'm changing that value for the key representing the element. Here? Okay. So, well, it's called the dictionary. You can, yeah, think of it as a set of mappings. If you'd use a set of, so if you use a square brackets or tuple, right? If I say 1, 2, 3, 4, so first of all, in square brackets, I cannot use a column, right? Right. So the best you could do is say use a pair, right? So you could say 1, 2, and that's my first mapping, right? The next one is 2, 4. That's the second mapping, and so on and so forth, right? So you would use a list of pairs now, right? So in principle, you do have the same information, right? So let's call this naive dict. All right. So the question is now, if I say naive dict and apply it to 1, what am I going to get? I would like to get 2, right? But I'm not going to get 2, right? This is the first element of the list, and this is what I'm going to get, right? Now, list is mainly sequential, right? It stores the order, and when it stores the order, right, the only way to retrieve an element is to scan through the entire list from one end to the other and find the key, right? So that's going to have much worse performance in terms of finding things. Dictionaries can uh, find things very, very quickly. Cool. So now, conversions. So I kept saying that a dictionary is a set of mappings, and when a mapping is a pair, so the conversion will always be two pairs of things, right? So if I say dict, what I have to provide here is a list of pairs, right? Out of a list of pairs, I can get a dictionary. Out of a tuple of pairs, which is essentially a tuple of tuples, I can get a dictionary. And out of a set of pairs, which is a set of tuples in the end, I can get a dictionary. Is that clear? I can't get a dictionary out of a single layered collection. I can't get a dictionary out of a set of numbers or a list of numbers or a tuple of numbers. I can only get it from a set of tuples or a list of tuples or a tuple of tuples. Clear? And the reverse is similar. Oh no, the reverse is so this is one very confusing thing. Always remember it, and right. Whenever I look at a dictionary and I consider it an iterable, it's the list of keys. So list applied to a dictionary will be the list of keys, and tuple applied to the dictionary will be the tuple of keys, and the set applied to the dictionary will be the set of keys. Right? It's kind of stupid, but it is what it is. Okay. All right. Remind me next time to go through list and set comprehensions, because it's a bit hairy and I don't have time now. I am going to talk a little bit about strings. All right, because these are easy. So we've already discussed this, right? We have two ways of constructing strings with double quotes and single quotes, right? And when I use double quotes as delimiters, so when I use them here, these are called the delimiters. This is a delimiter, and this is a delimiter. And at that point, I can use single quotes inside without any problem. Okay? And if I use this as delimiter, single quote as delimiter, here and here, I can use double quotes inside without any problem, right? Now, I might be crazy enough to want to use single quotes as delimiters and use single quotes inside, right? And in that case, we can escape them. If such an urge arises, which is generally recommended against, we can escape them by putting a backslash in front, right? So this typically is called an escape. Okay? Yeah, so so imagine Python reading from left to right. So it starts reading, here it says, oh, I've encountered a quote, it's the beginning of a string, and I keep going. Oh, there's a backslash. So whatever follows is definitely not the end of the string, right? So reads the single quote and goes, and again says, whatever follows this is not the end of the string. And now it sees an unescaped quote and says, this is the end of the string, right? And similarly here, right? You can do it for double quotes as well. All right. Now, strings are sort of sequences, so they will share certain properties similar to lists. However, they're immutable. And what we can put inside is only characters. All right? And you might think of these as being also characters, right? So we have 1, 2, 3, which is a number, and we have 1, 2, 3 in quotes, which is a string. What's the difference? Again? You cannot perform? Yes. Right? So they're encoded differently. Right? So think of a string as the sequence of key presses. All right? you're pressing 1, then 2, then 3, and that sequence of key presses is stored somewhere in memory, and that forms a string. And since there are many key presses, some of them being digits, any sequence of key presses can be stored into a string, right? Now, if I restrict myself to digits and I don't put them into quotes, what happens is that Python will look at them and will create out of them an entity that is of a different kind, and that forms a number. So whenever you see something like this, it's 1 and 2 and 3 are characters, and it's completely different from a list having both strings and numbers inside, right? So so strings have a lot less structure. However, they're a sequence of characters, right? But they're a sequence, and because of that, they're going to have length, right? So I can have length, right? And we can add them together, right? Remember, they're immutable. So unlike lists, they're immutable. But we can add them together, right? We can put a plus sign, okay? And we can access individual characters, right? And all the indexing schemes work. So we can take ranges, and this will form a substring, right? This will form a substring exactly on the same rules as if it were a list. Yeah, well, taken literally, I lied, right? So that's a good observation, actually. All right. So when I start an expression with a square bracket, that means a list, right? And if I have a list represented by square brackets, I cannot use the colon, right? So 1, 2 is going to be an error here. Yes. However, when the square bracket follows an expression, right, like this, right, then it is an indexing expression, right? And inside an indexing expression, I can provide a range. So this is very much legal. An expression, then it's indexed. I'm indexing something, right? So then I can even have 2 columns. Huh? Why? Oh, because it's 1, 2, that's 3, 5. Okay. All right. We have equality and this equality, right? So we can put the equal sign and check whether it's true or false. We have comparison, right? So you can think of strings, if one would come before the other in the dictionary, then one is smaller than the other. Okay. We have a lot of goodies in terms of strings because they're useful, right? So we can, for instance, capitalize a string. All right, so capitalization means that the first letter is turned into a capital. See, here it was a small letter, and here is a capital. All right, now let's take this crazy string, which some people make a point in writing online, right? They write posts like this so that it can annoy others. All right. So there's a function to get rid of that, right? So you can put your web page through a filter in Python and then display it the way you want it, right? That is called casefold. And notice that I'm every once in a while I'm encouraging you to use help and explore on your own, right? You can just go to the the prompt. So you can say, for instance, there for string, any string here, right? And you're going to get all the goodies, right? All the functions that exist, right? And you can see case fold here. So then you can say help of empty string dot case fold, right? And you get the what that function does, right? So that's a very useful way of exploring and figuring out and what is possible to do. And whenever you're thinking of that something is quite basic, it's quite likely that it's already implemented, right? So you don't have to implement it from scratch. You just have to try to find out what is the way of doing it. Right? It's probably just a function or a procedure name that you're missing. So you can convert them to uppercase, right, which is shouting, right? You can make them all small, right? You can make them into a title, all right? And very important thing that we will probably use later is we can split it into separate words. So with this, we could go and take a piece of text and find out how many times each word is occurring, right? Which would be a lot more interesting compared to counting occurrences in a list of numbers. Okay. So now that we have this, we can join them back. Instead of using spaces, we can use some other character, for instance, underscore, right? And then let's say we want a Python variable to create a Python variable out of string, right? If we put underscores, then it becomes a Python variable name. So we say which is the joiner, and that joiner will have a procedure called join, and here is our list, which we have obtained from the original string. So from this expression, we replace the spaces with underscore. We can find a word. So we'll get the index of the start of the substring, right? If that word doesn't exist, we're going to get -1. That again is traditional. It's, so returning -1 for not found is from the beginning of computing. All right. Index does the same thing as find, right? Just that one fails. One is silent, doesn't fail, so returns -1, right? But index yields error. So again, you have the choice of using one or the other. This one is the traditional one, right? Find is the traditional one. Index is, the modern approach, so to speak. We can count occurrences of any string, right? And this doesn't need to be a single letter, right? And we're going to get 4. We can replace anything by anything else. All right, and it will replace all the occurrences. Finally, we can split on a specific word, right? So you can partition, as opposed then of creating multiple, a list of multiple breakages. We can just create 3, right? So this one was going to go in the middle, and notice the space here is still exists, and the space here still exists. All right. So we can partition exactly one place. It will partition on the first occurrence. So if over appears many times, you just get the first one. Yes. So this is, it tries to find this word, and then it produces the before, the actual partitioning word, and then the after. Okay. If the word doesn't exist, then the last two elements are empty. You still get a triple, but the last two elements are empty. We can check whether a string ends with something, whether it starts with something, right? And we can swap case. So remember this string that has mixed case. We can exactly invert the case. We can check whether a string is purely alphabetic, only contains alphabet letters. And this is the case here, right? This AB is alphabetic. Spaces are not alphabetic, so if we go on this string, where we're going to get forms. Then A7 is not alphabetic. Okay, 4, 5, 5, 6. We can check for digits. 4, 5, 6 would be digits. So is digits is true. And then we have the so-called alphanumeric, letters plus digits, which are typically what we use in programming languages for identifiers. So this is a very typical way of checking whether a string is a valid identifier in a language. We can check if we have only lower letters. We can check whether it has only upper letters. And we can check whether it's space. In space, we include multiple characters. So there's the actual space, the space bar. There's the tab, right? So if I go in here and press tab, you can see that, right, the cursor moves, and if I delete, you see that every time it skips a number of spaces, right? So that's because there's an invisible character there. Okay, I'll be out in. Give me 2 minutes. Sorry. All right, so we're gonna stop here. So what I owe you is the rest. Remind me, please, to do the. In case I forget, remind me, please, to do the comprehensions. Okay, so I'm gonna